Welcome to the DPL Science presentation on the Introduction to Spacecraft Charging. DPL Science is a scientific research and engineering consulting company providing technical expertise in the space sector. The company provides engineering support to government and industry, produces technical training materials, and performs scientific research and development on space-related projects. This presentation is sponsored in part by the NASA Space Environments and Effects Program. At the end of this presentation, you will be able to answer the following questions. 1. What is spacecraft charging? 2. When is spacecraft charging detrimental and why? 3. How can we minimize the possibility of spacecraft charging and mitigate its effects? In this presentation, we will also take a look at some of the practical aspects of spacecraft charging work. In particular, we will take a look at some of the specialized test facilities that perform the different types of tests in the area of spacecraft charging. Please note that this presentation is an educational tool, intended solely as an aid to understand the phenomenon of spacecraft charging. Thank you for selecting this presentation. For any comments, we invite you to contact us through our website at dplscience.com. Since the 1970s, spacecraft charging has been actively researched, and there are many documented failures and anomalies attributed to spacecraft charging. While significant knowledge has been gained in how to protect spacecraft from charging, continuing technical advancement in the design and build of satellites requires ongoing effort in the study of spacecraft charging. This presentation introduces the basic concepts of spacecraft charging and explores the various tools and techniques used to control spacecraft charging. The presentation is intended for engineers, technicians, and managers involved in the design and build of spacecraft systems, and who would like to learn more about the phenomenon of spacecraft charging. The presentation is also suitable for aerospace engineering students. Here is the overview of the presentation. The section "The Sun" takes a look at some of the basic properties of the Sun and its role in spacecraft charging. The section "Spacecraft Charging" divides the spacecraft charging problem into three distinct components. It will be seen that the need for dielectric materials on spacecraft design is the primary reason why spacecraft charging must be addressed. The section "Mitigation Techniques" takes a look at some of the challenges of modern spacecraft design and how the challenges of mitigating spacecraft charging are successfully met. The section "Design Guidelines" presents a brief summary of some of the NASA design guidelines for minimizing both surface and internal charging. The section "Test Facilities" includes pictures and descriptions of several test facilities capable of performing spacecraft charging-related tests. The section "Publications" includes some suggested publications for further reading. The section "Conclusion" summarizes the work required in order to properly address the problem of spacecraft charging. Please note that this presentation is an educational tool. For specific applications, viewers are strongly advised to obtain further information from the many publications that are widely available. A few of these publications are mentioned towards the end of this presentation, while many others are available through professional organizations such as the American Institute of Aeronautics and Astronautics, the Institute of Electrical and Electronics Engineers, and space agencies such as NASA and ESA. This section takes a look at the Sun and its role in spacecraft charging. The space environment is a harsh environment. Rather than being an empty vacuum, space is filled with high-energy particles and radiation from the Sun. The picture shown here is a close-up of eruptions on the surface of the Sun. With each eruption, a large number of high-energy particles, as well as huge doses of radiation, are released. The total energy radiated by the Sun averages 383 billion trillion kilowatts, equivalent to 100 billion tons of TNT exploding each and every second. A well-known phenomenon of the Sun is the 11-year sunspot cycle. Basically, the magnetic field of the Sun flips its orientation every 11 years. Within these 11 years, we have 4 years of low solar activity, in which the frequency and intensity of the flares are relatively low. This is characterized by the image on the left. During years of high solar activity, the frequency and intensity of the solar flares are higher. This is characterized by the image on the right. In general, the period of high solar activity poses a greater threat to satellites. The period of low solar activity, however, can also be very dangerous to some satellites. In particular, it has been observed that there can be an increased number of very high-energy particles in geostationary orbit during periods of low solar activity. Communication satellites located in the geo-orbit are at risk here. This scaled picture shows the size of the Earth in comparison to a typical solar flare. A solar flare is much larger than the Earth. This image emphasizes the power of a typical solar flare. The Sun is massive. Its radius is about 109 times the radius of the Earth, and its mass is about 330,000 times that of the Earth. Over 1 million Earths could fit inside the Sun. The Sun is a very stormy body, with flares and eruptions occurring continuously. The Sun can emit huge quantities of plasma over several continuous hours. This process is known as coronal mass ejection. Since the 1970s, coronal mass ejections have been studied and are now known to be the most important driver of space weather. This picture shows the coronal mass ejection of October 2003, one of the largest flares ever seen on the Sun. The ring at the center marks the outline of the Sun. A disk is placed over the eye of the monitoring instrument to protect it from the intensity of the Sun. It also allows the ejections to be seen more easily. With each ejection, high-energy particles are released. These particles travel very quickly and have been dubbed solar wind because of their velocity. The solar wind, represented by the 6 white lines emanating from the Sun, affects the Earth's magnetosphere. The magnetosphere, represented by the pale blue lines, protects the Earth from being directly hit by the high-energy particles from the Sun. The solar wind exerts an incredible amount of pressure on the Earth's magnetosphere, compressing it on the Sun-facing side and stretching it into a long tail on the opposite side. Although the magnetosphere prevents most of the high-energy particles from directly hitting the Earth, some particles gain entry through cusps that are shaped like funnels over the polar regions. The presence of these high-energy particles is a threat to satellites. These charged particles accumulate on the spacecraft and become a problem when there is a sudden release of these high-energy particles. The energy contained in this sudden release may be enough to damage sensitive electronics on board the spacecraft. The process by which all orbiting spacecraft accumulate electric charge from the natural space plasma is called spacecraft charging. This section presents some of the effects of spacecraft charging and identifies 3 main areas of concern. Spacecraft charging can have varying degrees of effect, ranging from harmless phantom commands to catastrophic failure. ALSAT A3 experienced numerous phantom commands affecting its telemetry and attitude control systems. Energetic particles penetrated the electronic components, which caused bit changes in the electronic signals that led to the phantom commands. These commands appeared to the spacecraft as being sent from ground control and were therefore executed accordingly. In the case of ALSAT A3, the phantom commands were harmless, but it is possible for a phantom command to be harmful, for example, a command causing the spacecraft to point away from Earth. Anik E1 experienced a temporary disruption in service due to damage to the primary momentum wheel control shortly after an intense solar storm. Within 8 hours, however, the backup momentum wheel control was activated and service was restored. Anik E2 experienced a more serious disruption in service due to the same intense solar storm as experienced by Anik E1. Not only did the primary momentum wheel control fail, but the backup failed as well. 8 months later, the ground team was able to restore the satellite by using the thruster motors to keep the satellite stable and properly oriented. From then on, Telesat engineers would have to regularly send commands to the satellite to fire its 22 thrusters. The 8 months of repair and lost revenues cost Telesat about $50 to $70 million US. In 2003, Anik E2 would have to prematurely end its nominal mission due to the shortage of fuel. Then, of course, there's the catastrophic failure in which the satellite is completely lost. This was the case with the Chinese experimental weather satellite, Fenyang-1. It failed after only 39 days in orbit. The failure is believed to be caused by an electrostatic discharge, or ESD, on the attitude control system. An electrostatic discharge is the sudden, uncontrolled transfer of electrons from one material to another that has a different electrical potential. ESD can cause damage to spacecraft components by introducing large transient currents that cannot be sustained by the electronics. These cases are just a few of the many spacecraft charging anomalies recorded to date. NOAA's National Geophysical Data Center maintains a database of spacecraft operational irregularities due to the environment. These events range from minor operational problems to permanent spacecraft failures. The latest version of the database covers reports between 1983 and 1992. Why does spacecraft charging occur? Spacecraft charging occurs because of a combination of two things: high-energy particles found in the natural space plasma, plus ungrounded metal or floating metal, or high-energy particles found in the natural space plasma, plus the use of dielectric material. We will examine these three components separately: the natural space plasma, the floating conductor, and the dielectric. The first component as to why spacecraft charging occurs is the natural space environment. The existence of high-energy particles is a natural phenomenon. The Sun is an active body, with flares and eruptions occurring continuously. With each flare or eruption, a large number of high-energy particles is released into the space environment. All orbiting spacecraft encounter these high-energy particles. This diagram depicts the various satellites that have been launched by NASA, ESA, and their partners for the purpose of studying the space environment. Previous well-known NASA satellites include GOES and CRESS for studying the geosynchronous environment, and a series of DMSP satellites for studying the polar Earth orbit environment, among several others. These satellites produced a wealth of information about the space environment. The flux reaching the satellite is highly variable and difficult to predict. Modeling for spacecraft charging, therefore, uses worst-case scenarios. The flux reaching a given satellite surface depends upon the flux from the Sun, the Earth's magnetosphere, the satellite orbit and orientation, particle energy, spacecraft shielding, and other factors. Because many of these variables are difficult to predict, testing performed in the true space environment, if possible, is preferred. Satellites such as LDEV, CRESS, and SCATHA have successfully carried science and technology experiments that have resulted not only in a detailed collection of space environment data, but also information about the effects of the space environment on space systems, as well as engineering data to allow for the generation of design methods to control spacecraft charging. The second component as to why spacecraft charging occurs is the presence of a floating conductor. Since electrons are much more mobile in a conductor, a discharge from a floating metal can be more powerful than a discharge from a dielectric because more electrons are involved in the discharging process. For this reason, ungrounded conductors should be avoided. In cases where conductors cannot be grounded easily or inexpensively, it may be necessary to evaluate potential discharges and their effects. As a general rule of thumb, all metal should be grounded to the spacecraft structure, either directly or through a high impedance. If this simple rule is followed, it will not be necessary to worry about discharges from ungrounded conductors. The third component as to why spacecraft charging exists is the use of dielectric materials. Dielectric materials are abundantly used in spacecraft design as exterior surface materials, for example, on solar cells, optical components, RF components, and thermal blankets, and as interior spacecraft materials, for example, as RF or PCB substrates. To date, there are few materials that meet spacecraft charging requirements and still provide the other necessary properties. Because the use of dielectrics in spacecraft design cannot be avoided, it is important to understand the properties of these materials. Spacecraft charging can result in absolute charging or differential charging. Absolute charging occurs when the spacecraft, as a whole, acquires a net potential relative to the ambient plasma. If the spacecraft is all metal and in electrical contact, the entire spacecraft will be charged to the same potential. Absolute charging is nearly instantaneous, with characteristic periods on the order of microseconds. In most cases, absolute charging does not lead to significant detrimental effects. Differential charging can be caused by the presence of isolated components made of different materials. Typically, differential charging occurs after geomagnetic substorms, which result in the injection of high-energy particles into the magnetosphere. Differential charging also occurs when the satellite is partially illuminated by the sun, resulting in differential potentials between sunlit and shaded surfaces. Photoelectron emission causes the sunlit surfaces to be positively charged relative to the shaded surfaces. The difference in potential causes an electric field to develop between the two surfaces. Electric force fields can produce stress in spacecraft materials and can lead to detrimental effects on spacecraft. In general, spacecraft in geosynchronous orbit are more likely to undergo differential charging than spacecraft in lower orbits. Low Earth orbiting spacecraft which can develop significant differential charging are those that pass through the energetic Van Allen radiation belts or the South Atlantic anomaly. Also, the use of a high-voltage power system in low Earth orbiting spacecraft can increase the adverse environmental effects. Charging caused by high-voltage spacecraft power systems is sometimes referred to as active charging. There are two types of charging, surface charging and internal charging. Surface charging occurs on the exposed areas of the spacecraft, those parts that are exposed to the space environment. It is due to low-energy particles that do not have enough energy to penetrate below the surface and simply accumulate near the surface, typically about 2 to 10 microns below the surface. The exposed surfaces are either dielectrics or ungrounded conductors. Another term that is sometimes used to describe surface charging is shallow charging. In surface charging, energy is typically described in electron volt. It is a very small amount of energy. 1 electron volt is equal to 1.6 times 10 to the minus 19 joule of energy. It is the energy gained by an electron accelerated through an electrical potential difference of 1 volt. Larger units of energy are multiples of the electron volt. 1 kiloelectron volt is 1,000 electron volts. 1 mega electron volt is 1 million electron volt. Surface charging typically involves electrons with energies of several kiloelectron volt. Flux is typically described in nanoamps per centimeter squared. The energy of the charged particles causes the particles to continuously move. Moving charged particles create electrical current. The moving electrons create a negative current, and the moving ions create a positive current. Surface charging is a complicated process involving the interaction of the charged particles with spacecraft surfaces, typically leading to charged surfaces from tens of volts positive to tens of thousands of volts negative. The spacecraft surface potential depends on the balance achieved by the various currents striking or leaving the spacecraft surface. Backscattered electrons are those incident electrons that are reflected from the spacecraft surface with some loss of energy. Secondary electrons are emitted as a result of energy deposited by incident electrons or ions. The number of backscattered and secondary ions is very small, making them insignificant in the overall charge balance. Another source of electric current to spacecraft surfaces is the photoelectric effect. Photo-emitted electrons is the release of electrons from the spacecraft surface due to solar illumination. Equilibrium is achieved when the net current to the spacecraft surface is zero. At equilibrium, the charging process stops and the spacecraft reaches the equilibrium charging level, also known as the floating potential. Because electrons are much more mobile than ions due to their smaller mass, the electron flux dominates so that the negative current is larger than the positive current. Consequently, charging typically leads to negative floating potential in the order of the electron energy. Internal charging is caused by high-energy particles which have sufficient energy to penetrate the surface and deposit charge inside the spacecraft. The charge is deposited within dielectric materials or on ungrounded conductors. The depth of penetration depends on the energy of the incident particle. Other terms that are frequently used to describe internal charging include deep charging and bulk charging. The electron environment for spacecraft charging evaluation is normally defined in terms of electron flux versus electron energy. The unit of the electron energy is the electron volt. The electron flux corresponds to the rate at which electrons pass through or into a surface element, with the time unit explicitly specified. The unit of the electron flux can be expressed as the number of electrons per square centimeter per second per steradian. There are 4 pi steradian in a sphere. Internal charging is especially hazardous because dielectric discharges may directly feed into a victim pin or wire, thus causing the possibility of major system upsets or catastrophic failures. Three very important properties of dielectric materials that must be considered when looking at spacecraft charging are electron yield, resistivity, and dielectric strength. Electron yield is a measure of the number of electrons that leave a surface for each incident particle that impacts the surface. The electron yield depends on the material and on the incident particle species, energy, and trajectory. Together with the particle flux, the electron yield determines how much charge will accumulate on a spacecraft element. Resistivity is a measure of charge distribution within the material. Resistivity measures the charge transport and hence determines the redistribution and dissipation of charge. The higher the resistivity, the poorer the charge dissipation. In materials with high resistivity, charge remains for a longer period of time. Dielectric strength is the voltage level at which the dielectric material physically breaks down. Dielectric strength is a measure of the maximum charge that can build up before discharge occurs. The use of dielectric materials in spacecraft design is a concern because of 1. Charge deposition. Electric charge can build up inside or on the surface of a dielectric. 2. Charge migration. The resistivity of dielectric materials can be very high, so that charge will remain in the dielectric for a long period of time. And 3. Electrical breakdown. When the charge buildup or electric field exceeds the dielectric strength of the material, a discharge occurs, potentially causing catastrophic failure to the satellite. The combination of incident charge and emission determines the charge imparted to a material. The charge deposition is largely driven by the space environment. The depth of deposition is mostly determined by the energy of the incident particles. The emission is largely a material's property. Because the mass of the electron is 4 orders of magnitude less than the mass of the ion, electron emission, as opposed to ion emission, dominates the process, because lighter particles move faster. Both deposition and emission depend on many complicating factors, such as charging history, contamination, and synergistic effects of different incident particles and particle energies. Resistivity determines the charge migration, or the flow of charge within a material, and hence the extent of charge buildup. Again, resistivity is largely dominated by the flow of electrons as opposed to ions. For materials with low resistivity, such as conductors or semiconductors, the flow of electrons is rapid and charge will flow to ground. For materials with high resistivity, such as insulators or dielectrics, the flow of electrons is slow and charge can accumulate within the material. The time it takes electrons to leave the material can be estimated using the decay time. Typical orbital periods of near-Earth satellites range from 1 hour to 1 day. If the charge decay time exceeds the orbit time, not all charge will be dissipated before orbital conditions act again to further charge the satellite. In such a case, charge will continue to accumulate within the material. This plot shows the decay time versus material resistivity. From the plot, we see that materials with resistivities greater than about 10 to the 17 ohm centimeter can present a risk for spacecraft charging anomalies because the decay time exceeds 1 hour. More serious charging problems occur for resistivities greater than about 10 to the 18 ohm centimeter when the decay time exceeds 1 day. Deposited charges induce an electric field within the material. As charge continues to accumulate within the material, the electric field intensifies. If the electric field exceeds the dielectric strength of the material will physically break down. Breakdowns result from a large concentration of charge or a small thickness in the material. Most common spacecraft dielectrics may break down when their internal electric field exceeds 10 to the 7 volt per meter. With the physical breakdown of the material, a discharge can occur. A discharge produces a broadband electromagnetic field or current that can couple into spacecraft electronics, causing upsets ranging from minor phantom commands to catastrophic failure. The problem is that dielectric materials are used extensively in spacecraft designs. To illustrate this point, we will take a look at the ENVISAT satellite. ENVISAT is a remote sensing satellite built by the European Space Agency and launched in 2002. It is one of the largest and most advanced Earth observation satellites of its time. ENVISAT is an example of a new generation of satellites. It has an advanced synthetic aperture radar antenna, which is essentially a patch antenna or a printed antenna using dielectric material. In most other satellites, antennas are basically grounded metal structures, but the patch antenna is composed of an array of metallic patches on a dielectric substrate, with a significant portion of the dielectric substrate that may be exposed to the harsh space environment. Second surface mirrors are commonly used on spacecraft designs. To prevent surface charging, a thin layer of grounded conductive coating, such as indium tin oxide, may be used. However, internal charging beneath the ITO coating, where Teflon, quartz, or borosilicate glass is present, is a possibility. Sunshield is another common material used on spacecraft designs. Like the mirrors, a grounded outer conductive coating will help to prevent surface charging, but internal charging on dielectrics beneath the coating is possible. The same is true with the thermal blanket, another commonly used material on spacecraft designs. Solar arrays are commonly used to generate electrical power needed by the spacecraft electronics. Dielectric cover glasses protect the solar cells. Solar array design requires the arrays to be ungrounded. Therefore, a ground path cannot be implemented to help remove charge away from the dielectric. A satellite may also require that some of its electronic instruments be mounted outside the spacecraft structure. Traditionally, the electronics are mounted inside the spacecraft structure, where they can benefit from the electrical and mechanical shielding provided by the bus. This illustration of ENVISAT shows 10 sophisticated electronic instruments mounted on the outside of the spacecraft structure. The need to mount electronic instruments outside the spacecraft structure and the use of a printed antenna on dielectric material illustrate the types of new challenges that spacecraft designers must be ready to face. Materials like second surface mirrors, sunshields, thermal blankets, and solar array cover glass, although commonly used on most spacecraft designs, cannot be taken for granted. The constant evolution in spacecraft design and technology means that spacecraft designers must always be mindful about what dielectric materials are being used and where. Discharges can have several effects. Discharges can cause physical damage to the dielectric material, thereby altering the properties of the dielectric. This is a photo of a discharge on a piece of mylar taken in Professor Balmain's laboratory. The discharge has a tunneling effect. The discharge path is just beneath the surface of the mylar. At various points along the discharge path, there are blowout holes. These blowout holes are due to the intense heat of the electrons, which cause the surface of the mylar to vaporize. Here we have a picture showing the burn marks observed on the solar array of ESA's Eureka satellite. The burn was caused by a sustained arc discharge. Sustained electrical arcs are initiated by the space plasma, then powered by the solar rays themselves. In this case, the damage is produced by active charging, caused by the high electrical potentials of the power system itself. Solar arrays are composed of solar cells in series with each other, forming a string. Additionally, the strings may be connected in parallel to produce the entire solar array power. An arc on one solar array string can couple to an adjacent string and continue to be powered by the solar array output until a permanent electrical short is produced. Sustained electrical arcs can damage entire solar array strings in just a few seconds. Sustained arcs can lead to power surges or power interruption, or a complete failure of the solar array. Sustained arcs can also introduce contaminants in the vicinity of the satellite, interfering with the proper operation of nearby instruments. Discharges can also generate conducted emissions, a form of electromagnetic interference, or EMI. An EMI is a disturbance that interferes with the proper operation of electrical equipment. Large discharge-induced transient currents can flow in the wiring harnesses and cables, propagating directly into electronics boxes and potentially damaging the electronics. Discharges can also generate radiated emissions, another form of EMI. The level of radiated E-field may be high enough to affect sensitive units, or this radiated E-field may find its way inside harnesses and change into a conducted emission. In any satellite design program, then, it is important to make an inventory list of all dielectrics being used and where they are used. Since the use of dielectrics cannot be avoided, it is important to evaluate the likelihood of a discharge from each dielectric and location. If the dielectric is likely to discharge, then assess the potential damage that can result from a discharge. If the discharge is potentially damaging, then include precautions to avoid damage or failure where necessary, for example, adding filters at the input of sensitive electronics. Finally, it is also necessary to check for any ungrounded conductors and to take the necessary corrective action. The spacecraft charging specialist is a valuable technical authority on any space program. The specialist would be responsible for tasks such as defining the space environment. The specialist would define the environment to which the spacecraft will likely be exposed in terms of electron energy and flux. This is not an easy task. It involves much research and study on data that is currently available, as well as keeping abreast of the latest findings in this field. The specialist could expect to generate several iterations of data before coming up with a set that is deemed to reasonably define the space environment that the spacecraft may encounter. The specialist would also provide design guidelines and their interpretation. This involves research again into published existing design guidelines. The specialist would take these general guidelines, modify and adapt them to fit the design of the particular spacecraft. Essentially, the specialist would work with spacecraft designers in implementing ways to reduce or eliminate spacecraft charging and its effects. The specialist would also conduct spacecraft charging analyses and tests. In reality, the spacecraft will not be designed to conform to all the spacecraft charging design guidelines and requirements. In cases of deviations, the specialist would perform analyses or tests to make sure that these deviations are acceptable in an ESD sense. The specialist would also provide recommendations and ongoing support. Issues can arise at any time within a program, from conceptual design to spacecraft integration and test. The specialist must be able to support the program in its entirety. Historically, power systems on space vehicles have operated at the nominal 28-volt DC, a standard inherited from the aircraft industry. At such low voltages, interactions with energetic particles in low Earth orbit are negligible and have not been a large consideration in spacecraft design. Located in the low Earth orbit, the International Space Station is the largest and most complex international scientific project in history. Led by the United States, the space station draws upon the scientific and technological resources of 16 nations. Several pressurized modules allow an international crew of up to 7 astronauts to live and work in space. Because of its enormous structure, mass was a huge consideration in the design. In order to reduce the overall system mass, the space station has been designed to operate at lower currents and higher voltages. Lower currents allow the use of smaller size cables, resulting in mass savings and reduced power loss. Low currents, however, are compensated by operating the space station at high voltages in order to supply sufficient power to the electronics. The space station power system is the responsibility of the NASA Glenn Research Center. The power system is designed with high-voltage solar arrays that typically operate at output voltages of 140 to 160 volts. Almost an acre of solar panels is required to provide electrical power to 6 state-of-the-art laboratories. The space station grounding scheme electrically ties the habitat modules, structure, and radiators to the negative end of the solar arrays. Early testing indicated that the high voltages and exposed conducting surfaces across the solar arrays could cause the space station structure to charge to a significant negative potential relative to the ambient space plasma as a result of active spacecraft charging. This charging could lead to arcing, damaging critical spacecraft surfaces, as well as presenting a hazardous environment to an astronaut performing a spacewalk. In order to control charging on the space station, NASA Glenn designed a plasma contactor that emits electrons collected by the solar arrays. When this emitted plasma sees the ambient space plasma at a different potential, electrons stream between the two plasmas to equalize their potentials, controlling spacecraft charging in a self-regulating manner. The plasma contactor reduces the floating potential at all points on the space station to within plus or minus 40 volts of the ambient space plasma, ensuring an arc-free environment for the astronaut performing extravehicular activities. This section describes some basic design guidelines to be followed in order to minimize the effects due to surface and internal charging. NASA has published technical paper 2361, which includes several guidelines to follow in order to minimize surface charging. Here are some basic guidelines. Exterior surface materials. Ideally, all exterior surfaces should be conductive and grounded to the spacecraft structure. But insulating materials are often needed for thermal or other reasons. If it is not possible to use conductive materials, then use partially conductive materials. Again, make sure that these materials are grounded to the spacecraft structure. Partially conductive means that the materials should have surface resistivity of less than 10 to the 9 ohms per square, or volume resistivity of less than 10 to the 11 ohm centimeter over their full service life and temperature range. Grounding. Again, the simple rule is to avoid floating metals. All conducting elements should be grounded, either directly or through a charge bleed-off resistor. Shielding. Enclosures for electronics and the main spacecraft structure should be designed to provide a continuous physical and electrical shield to protect all units, cables, and harnesses. Limit the number of holes and the size of apertures in order to prevent high-energy particles from finding an easy way into the electronics. Design the enclosures to be electromagnetically tight, that is, a Faraday cage, so as to protect electronics against high levels of radiated E-field from a discharge outside the unit. Use grounded meshes, EMI gaskets, and appropriate depth-to-diameter ratios for holes. Procedures. Apply proper handling, assembly, inspection, and test procedures. Proper techniques are required to prevent contaminating the materials with dirt and debris. The introduction of foreign materials can alter the resistivity of the material, often making it worse. Thin coatings can be fragile, and mishandling the units can cause cracks invisible to the eye. Cracks in a conductive coating can become open circuits, leading to floating metal. Proper test procedures are also needed to ensure electrical continuity of the grounding system. NASA has published Handbook 4002, which includes several guidelines to follow in order to minimize internal charging. Here are some basic guidelines. Orbit selection. If possible, avoid orbits and altitudes where internal charging is an issue. This is a plot taken from the handbook. It is a simplified plot comparing the internal charging hazard levels for the different orbits. The x-axis indicates the orbit altitude, and the y-axis indicates the inclination angle. Regions of low internal charging hazard will be marked in green. Regions of medium internal charging hazard will be marked in yellow, and regions of high internal charging hazard will be marked in red. Low-altitude orbits are relatively safe from internal charging. Even the polar orbit, which is at low altitude, high inclination, is in this green region, despite frequently encountering high-energy particles in the polar horns and the South Atlantic anomaly. At higher altitudes, the hazard level increases to medium. For geosynchronous orbits, which are at about 30,000 kilometers, the level of internal charging hazard is high. This high hazard level for the geo environment is why the majority of spacecraft charging research and studies performed to date have largely been focused on geo spacecraft. Shielding. Provide adequate aluminum protection. Shield all electronic units with sufficient aluminum equivalent thickness to limit the number of high-energy particles that can penetrate through the shield. The handbook recommends a minimum shielding of 110 mil, or about 3 millimeters, of grounded aluminum equivalent for geo orbits. Grounding. Again, the simple rule is to avoid floating metals. Ground all metallic elements either directly or through a bleed path. Dielectric materials. Limit the use of excellent dielectrics. Materials such as Teflon, Kapton, and FR4 are excellent for storing charge. Limit their use, especially in large blocks. Use leaky dielectrics, for example, those with resistivity of less than 10 to the 12 ohm centimeter or 10 to the 12 ohms per square over mission life. Electric field. Keep dielectric fields below 100 volts per mil, or 4 times 10 to the 6 volt per meter, as a rule of thumb. Cables and harnesses. As much as possible, place all cables and harnesses inside the main spacecraft structure and route them away from apertures. Cables and harnesses outside the spacecraft structure may need additional protection. Filtering. Provide filters at the entrance of ESD-sensitive circuits. Provide filters also for cables entering the Faraday cage of the spacecraft structure. This is to prevent ESD noise from entering the structure. Thermal blankets. Ground all metal layers together and ground the blanket to the spacecraft structure. The same is true for sun shields. What happens when a design guideline cannot be followed? What happens if a patch antenna is required, with a significant portion of the dielectric substrate exposed to the harsh space environment? And what if the resistivity of this dielectric far exceeds the NASA recommended guideline? In this case, it becomes extremely important to perform analyses or tests to validate the use of the dielectric. It is important to assess the likelihood of a discharge from the dielectric and the potential damage it can cause. But analyses and tests are rarely straightforward. Here are some of the problems typically encountered. Material properties. Often there is not enough information about the material properties in order to do a proper assessment. As mentioned earlier, one important parameter is material resistivity. Volume resistivity is often simply given as greater than some number, but the spacecraft charging specialist needs a more accurate value. Is it 10 to the 15 ohm centimeter? Is it 10 to the 18? Or is it 10 to the 20? Manufacturers usually do not have the capability to provide accurate values because the resistivity is higher than that which can be accurately measured using conventional test methods. Manufacturers are often limited by the test setup or the measuring equipment. Still, in many cases, manufacturers do not provide any information at all. At times, standard resistivity tests tabulated for other applications are inappropriate for spacecraft charging applications. For example, resistivity measurements of good insulating materials are often better determined by charge decay methods than standard IV curve measurements. And what happens at cold temperatures? Resistivity, when it is available from the manufacturer, will usually be given at ambient. But what happens if the operational temperature of the dielectric is at minus 60 degrees C? What is the resistivity at this cold temperature? It is known that the resistivity can increase with a drop in temperature, but by how much? Breakdown voltages are sometimes provided by the manufacturer, but this information is not always available. Furthermore, actual breakdown depends on the geometry of the sample, the incident flux, and energy distribution, as well as charging history. Likewise, there is often insufficient information on the electron emission properties of spacecraft materials. Emission properties can be affected by contamination, materials degradation, charging history, and incident particle flux and energy distributions. Actual environment. What is the actual space environment to which the spacecraft will be exposed? How can the space environment be accurately defined in terms of electron energy and flux? What is the stormy environment? How often will a storm occur? How will the flux change after a storm? These questions are not easily answered. Limitations on the test setup. When it comes time to do a test, there will be test limitations. For example, a test setup may not be able to supply the required current density or provide a spectrum of energies. Sensitivity of the victim circuit. This information may not be readily available for various reasons. Perhaps the victim circuit has not yet been EMC tested. Safety margin. How much margin is required? Some large spacecraft manufacturers, based on their internal tests and experience, determined that the surface potentials should not be greater than 500 to 1000 volts. What if an analysis or test shows that a material may charge up to 1500 volt potential, but its breakdown is at 10 kilovolt? Is this acceptable? List of dielectric materials. It may be very difficult to get a full list of all dielectric materials used in all units, for example, from subcontracted units. Temperature profile. To perform a full surface and internal charging analysis or test, a temperature profile of the spacecraft is required. Temperatures of all surfaces, units, and dielectrics are required. This can be quite involved. And accounting for parameters such as radiation and E-field-induced conductivity, the presence of ions, grounding schemes, etc., is difficult, but these issues do affect the analyses. This section provides photos and descriptions of several spacecraft charging test facilities. In an ideal world, each spacecraft would be extensively tested under simulated space environmental conditions that it is expected to encounter. Of course, such extensive testing of the full spacecraft system is neither practical nor is it economically viable. The best compromise available is a combination of materials and components testing in representative space environments, along with detailed modeling of the spacecraft system using modeling codes such as NASCAP, SPENVIS, or SPARCS. This section provides photos and descriptions of several spacecraft charging test facilities. Each facility provides unique capabilities to make measurements of charging properties, including charge deposition, charging profiles, electron emission, resistivity, and discharge under a variety of simulated space environment conditions. Different facilities allow for testing of individual materials or component systems. Often, testing at more than one facility provides a clearer picture of the complex issues involved. SRI International, located in Palo Alto, California, has a spacecraft charging test chamber. The SRI facility is used to study surface charging. Samples are exposed to low-energy electrons and high flux, with the electrons at a single fixed energy. The test setup measures the surface potential at various points on the sample and captures discharge currents and the associated E-field. The test facility can accommodate large samples and component testing. The team is headed by Richard Adamo. His engineer is Victor Aguero, and their technician is Bob Sharpless. They are pictured here in front of their spacecraft charging simulation facility. The test setup includes a vacuum chamber where the test sample is placed, and a multipactor source for generating the electrons. The sample is mounted inside the bell jar onto a grounded cold plate. The bell jar is sealed, brought to vacuum, and to the desired cold temperature. The sample is then irradiated with a beam of electrons from the multipactor source above. A potential scanner sweeps above and across the sample so that the surface potential can be recorded along different areas of the sample. There is also an observation window where discharges can be viewed physically. This picture is a close-up of the electron source. It uses the multipaction principle to generate the electrons. The advantage of using the multipaction approach is that it produces an electron source with a large surface area. Because of this, the setup can accommodate samples up to about 25 by 25 square centimeters. The electron source irradiates the entire sample with uniform beam density. The setup also includes an E-field probe to measure the radiated E-field of a discharge. An oscilloscope may also be added to the test setup as well to capture the profile of the discharge current. Test conditions include electron energy up to 30 keV, which is suitable for surface charging tests, current density up to 30 nanoamps per centimeter squared, vacuum, and cold temperatures with the temperature of the cold plate down to about -60 degrees C. The main features of the SRI facility include 1. The observation window, whereby one can witness the discharge in real time. 2. The electron source with uniform beam density over a large area, thereby allowing the setup to accommodate a large sample size. And 3. The E-field probe in the setup to measure the radiated E-field of a discharge. Located in Hampshire, England, Kinetic has an internal charging facility known as REEF, Realistic Electron Environment Facility. At REEF, investigations on the susceptibility of circuits and materials to ESD events and how to overcome these problems are carried out under realistic space conditions. Internal charging effects can be studied with discrete control over electron flux and temperature under ultra-low pressure conditions and over long timescales. The facility uses a strontium-90 source to simulate the energetic electron environment found in geostationary and medium Earth orbit. Key areas of study which may be carried out at REEF include materials testing, electrostatic discharge studies, component anomaly studies, and total dose investigations. REEF is designed primarily to study the charge distributions and discharging of material samples and components subjected to high-energy electrons. To learn more about the facility, visit the Kinetic Space Information Systems website. Contact details for the technical staff are listed there. ONERA, located in Toulouse, France, operates a number of laboratories for radiation and spacecraft charging studies. Among these laboratories are the CEDRE and SIREN test facilities. These facilities focus on charge distribution and discharges arising from surface and internal charging. The CEDRE facility is used to study charging and discharging characteristics of dielectric materials as well as radiation-induced conductivity. Test conditions include monoenergetic electron beam of 3 to 35 keV, current density from 0.05 to 5 nanoamps per centimeter squared, vacuum to approximately 10 to the minus 6 torr, temperature of the sample holder from minus 180 to plus 120 degrees C, and sample size up to 20 by 20 square centimeters. The CEREN facility is used to study surface and internal charging on spacecraft dielectric materials. Test conditions include spectral distribution of electrons from 10 to 400 keV that can be tailored to approximate the flux found in LEO, GEO, and polar Earth orbit. Current density from 0 to 2 nanoamps per centimeter squared. Vacuum to approximately 10 to the minus 6 torr. Temperature of the sample holder from minus 180 to plus 120 degrees C, and sample size up to 20 by 20 square centimeters. A major test facility is operated by the Materials Physics Group at Utah State University in Logan, Utah. The facility is directed by Professor J.R. Dennison and run by a dedicated group of postdoctoral associates, graduate research assistants, and undergraduate students. Most test facilities focus on the charging and discharging of materials and components, whereas the Utah State Test Facility focuses on material properties related to surface charging. The facility measures material properties such as electron emission yields from incident electrons, ions, and photons, emission spectra, resistivity, and dielectric strength. Utah State University maintains 4 vacuum chambers with extensive space environment simulation capabilities. The primary test chamber at Utah State is an ultra-high vacuum chamber used for performing surface charging-related tests. The chamber includes temperature capability and simulates solar irradiation, electron flux, and ion flux found in space. Electron sources include 3 guns providing monoenergetic electron beams of about 50 eV to 30 keV, with electron flux ranging from 1 picoamp to 1 nanoamp per centimeter squared. 2 other guns provide monoenergetic ions in the range of 0.1 to 5 keV. The chamber is also equipped with a variety of broadband and monoenergetic light sources, covering a full range from the mid-infrared through ultraviolet. The sample stage is visible through the viewport and holds 11 samples that can be positioned in front of various sources and detectors, and is detachable for rapid takeout and changes. Utah State University also operates a second, smaller, ultra-high vacuum chamber dedicated for studying electron emission. Recent developments using pulsed beam technologies have extended the capabilities at Utah State to include studies of electron emissions of highly insulating materials. Such measurements are very difficult since emission properties have been found to change appreciably due to accumulated charge. Experiments at Utah State found measurable changes in electron yields due to as little as 100 femtocoulombs per square centimeter. While the sample is bombarded with a beam of energetic particles, a Faraday cup detector is rotated about the sample, detecting the energy and angular distributions of the secondary electron yield and energy spectra for emitted electrons. The chamber has also been used to study the effects of sample bias and contamination on the electron yield and emission spectra. A third high vacuum chamber is used for measuring dielectric resistivity using the charge storage method. This test method has been found to be appropriate for dielectrics with resistivities greater than about 10 to the 15 ohm centimeter and more applicable to conditions experienced by spacecraft insulators. The chamber is designed so that up to 32 samples on a rotatable carousel can be tested simultaneously in a controlled, stable vacuum environment for the duration of month-long experiments. The charge on each sample is measured using the TREC charge probe. Temperature range is approximately -100 to +100 degrees C. This photo shows the interior of the charge storage chamber. We see the 32 sample rotatable carousel, the sample holder, the charge probe assembly for detecting the voltage on the sample, the sample cover manipulator to prevent accidental discharge of sample surface charge, and the electron gun port. The rotatable carousel allows charge to be deposited separately on each sample and to be measured separately by the TREC probe. A fourth, smaller vacuum chamber is used to measure resistivities of moderate insulators using standard constant voltage test methods. The chamber allows tests to be conducted in a low-noise, temperature-controlled vacuum environment over periods of hours to days. This section includes some suggested publications for further reading on spacecraft charging. General references, engineering guidelines, and handbooks, as well as other technical references, will be introduced here. NASA has published some excellent documents that provide a general overview of spacecraft charging. One such document is entitled Spacecraft Environments Interaction: Protecting Against the Effects of Spacecraft Charging. Another such document is entitled Failures and Anomalies Attributed to Spacecraft Charging. In addition to a good general overview on spacecraft charging, it also contains an extensive list on spacecraft anomalies and failures due to spacecraft charging. This extensive list helps the reader appreciate the severity of the spacecraft charging problem. Several engineering guidelines or handbooks are available to the spacecraft designer and builder. For technical details on surface charging, there is NASA Technical Paper 2361, Design Guidelines for Assessing and Controlling Spacecraft Charging Effects. This paper provides design guidelines for minimizing or preventing surface charging and its effects. Although written in 1984, it is still widely used today. For technical details on internal charging, there is NASA Handbook 4002, Avoiding Problems Caused by Spacecraft On-Orbit Internal Charging Effects. This paper provides design guidelines for minimizing or preventing internal charging and its effects. The recent emergence of high-voltage, low-Earth orbiting spacecraft and their susceptibility to solar array arcing has prompted NASA C to produce an additional guideline. The document Low Earth Orbit Spacecraft Charging Design Guidelines highlights mitigation techniques to prevent spacecraft arcing on LEO solar arrays and other systems. ESA is developing a European guideline and handbook that will exist in two forms, a hard copy as well as an interactive electronic version. In the interactive version, equations will be solved and the results dynamically generated. Look for its upcoming release at the Kinetic Space Information Systems website. More detailed technical references are available on specific topics related to spacecraft charging. The Charge Collector is a compilation of spacecraft charging-related products offered by NASA C. Here you will find some of the very latest spacecraft charging information, including databases, reports, tabulated data, and design guidelines. U.S. citizens can apply for access to this information by filling out the Product Access and the Software Usage Agreement forms, which can be found on the NASA C website. Non-U.S. citizens must first apply for an international agreement through NASA headquarters. Every few years, the spacecraft charging community holds a spacecraft charging conference. Responding to the request of the many participants at the 8th Spacecraft Charging Technology Conference in 2003, NASA compiled all papers presented at previous conferences and have made them readily available to the entire community. Proceedings from these past conferences are available at the following website. The French space agency, CNES, has put together a collection of various spacecraft charging papers, most of which are written in French. For those who would like to read more about spacecraft charging in French, there is the text entitled Space Environment, Prevention of Risks Related to Spacecraft Charging. This is the conclusion summarizing the work required in order to properly address the problem of spacecraft charging. Despite years of studies and the knowledge gained in the area of spacecraft charging, there are still spacecraft anomalies being experienced today that are attributable to spacecraft charging effects. Dielectric materials are found throughout the spacecraft, and it is not always possible to provide adequate shielding. As well, spacecraft technology is moving towards more ESD-sensitive devices and lighter, less shielded structures. Spacecraft charging is likely to continue to cause problems in the future, so the studies must continue. It is important to continue research in this area so that current guidelines and standards can be improved. One key factor required to properly address spacecraft charging is the definition of the natural space environment. It is important to be able to define the space environment more accurately in terms of particle energy and particle flux. Many studies have been performed for the geo-environment, and these studies should continue. Studies for the lower Earth orbits are also necessary. Spacecraft designs such as ENVISAT, which is located in the polar Earth orbit, demonstrate the need for such data. Another key factor required to properly assess spacecraft charging is the dielectric material properties. Often, there is not enough information on the dielectric materials in order to properly assess whether or not the material will discharge, and if so, how much damage the discharge will cause. NASA publications and other references contain some information on properties of basic dielectric materials, but often a variation of those materials is used in the design. Any variation to the material can easily alter the resistivity, dielectric strength, and charging characteristics. Material testing is an important part of spacecraft charging evaluation, and the work here must also continue. Spacecraft charging is a fascinating topic, combining both science and engineering, and tests and analyses. Despite the great advancement the scientific community has made in this area over the last 3 decades, new technologies and new materials in spacecraft design require ongoing effort towards building ESD-free satellites within reasonable costs. Technical information for this presentation was obtained from the following sources. DPL Science would like to thank the following organizations and individuals for their valuable assistance.